Thanks for joining us again for this session. This is probably our largest summit that we've had to date, and we have more than 5,000 registrations. So thank you for taking the time to join us here today. So just some housekeeping items that we have for this course as we start off. We have a lot to cover. We only have about 90 minutes, so I'll just go through it pretty quick. Yeah, all sessions will be recorded, and the recordings will be made, as I mentioned, at distributedsql.org, as well as in the course player that I was showing you previously for the link for university.yugabyte.com for this specific virtual training. We'll upload the recording there, and it will be made available for download as well. Cool. Some common links, some things that might be helpful to you as you're joining and wanting to learn more about distributed SQL. We have our community Slack that you can join us. If you're looking for a sample set on our docs, we have a download for an old Microsoft Access database that's been ported over to Postgres called Northwind. That's pretty decent. pgadmin, GitHub, if you want to download, yugabyte.com, and then we have YugabyteDB Manage. I'll show you a couple of these links as we go through this presentation here, but let me just actually do that as we start. If you want to, no caps. If you want to go to download.yugabyte.com, you're most certainly welcome to. This is for folks who are interested in just getting Yugabyte up and running on their local machine. That could be Mac, Linux. If you're running Minikube or Kubernetes, you can do that as well. There's an example using Minikube in Helm. If you're on a Windows desktop, you may have access to a Ubuntu subsystem. Some of you probably have already installed that. Then you could run Linux in that subsystem setting. I think there are actually more than Ubuntu, those types of settings now. But regardless, if you're not, you can use Docker. So if you're not familiar with Docker, it's pretty straightforward, easy to install. A lot of people use it for virtual machines and containers. So it's easy to do. So don't worry about using Docker. It's safe, it's sound, and you can pull the latest build that we have here. Yeah, so if you want to get started up and going, just on this download play, just real quickly, I'll just highlight the fact that we have different types of releases for YugabyteDB, which is an open source distributed SQL database. And mostly what you'll see here are minor versions for a major version release. And the way our versioning works is our even versions are essentially what you would describe as stable or generally available, GA versions. And then our preview versions are going to be odd releases. So 2.15 is our newest and latest, right? So it's a preview release. Some people might want to call it that, beta will call it preview, and so on and so forth. Yeah, so you can go there. A great place to get started. If you're interested in deploying YugabyteDB core, that's what we refer to as our open source database. You certainly can do that within AWS, Google Cloud, Microsoft Azure. You are another Kubernetes operator, such as one hosted by Red Hat. And pretty much across the board, you'll see the same sort of CLI tools for the different public cloud providers. And we'll include Terraform if you want to use that, and then specific types of services that they're using, like Kubernetes services or Google Kubernetes or AWS service. They're all pretty much the same thing. If you're using any of these forms, for example, for Terraform, they're like, you don't have to put in anything real. It's all client side if you did, but if you're worried, all this is going to do is just generate, right? So there's no server-side script, but if you're worried or concerned about the security, like your AWS keys and like, probably shouldn't put it in, but then you can just copy this and then modify as needed, okay? All right. And then I would say the other option that we certainly have for you is YugabyteDB Managed, and that's pretty easy to sign up for. You just go to cloud.yugabyte.com and you can just sign up. There's no credit card required. You can sign up with essentially with your Google account or your GitHub account or even LinkedIn. So just like you do at the university, I don't think we have GitHub set up yet. We have Facebook, but anyhow, any one of these SSO sort of single sign-on accounts, just specify your company, email address, first name, last name, password, and so forth. Say what country you live in and so on, and that you're human, and you'll be ready to go. And there's a sandbox offering, which is what formerly referred to as free tier, where no credit cards required, and you can just kick the tires, get things going on your own. And I think you get up to something like, I want to say about 12 million rows or something. It's a single node sandbox, but it's a pretty good way to get started, especially if you're rapidly building an application and need a database. And that what's going to be distributed in the future, you can certainly then migrate, so to speak. Migrate's probably the wrong word, but upgrade, quote unquote, your sandbox into a 3-node cluster. And we'll talk more about what that looks like in different topologies as we go through this presentation. Okay, so back to my presentation, and then we'll go into some demos here. So let's see if this is working. There we go. All right. So yeah, those are things that I wanted to cover. And then the last here we have is Yugabyte, a GitHub. I'll just do that, open a GitHub real quick. And let's see, just to give you some reference here. This is our GitHub repository for the YugabyteDB, the open source version, but under the parent directory, probably. You won't see this. I've signed in my local account. We have a lot more just that we have available to you, but there's a ton of things that you might want to be interested in. Like, for example, oh, I want to use a JDBC driver for YugabyteDB that's aware of cluster topologies. Here's the JDBC YugabyteDB. You'll see this one. It says, oh, we got something new. Use the Postgres JDBC, so it's been renamed. But you can go here, and what we typically in all of our GitHub repositories that are publicly available, we'll have a good README. We'll have some samples, ways to get started, how to build things if you need to. If you want to do that, you're on your own, how to use the driver, and so on and so forth. So it's a great place, especially if you're looking for samples. You want to run a sample app, you want to run sample workloads. Like, pretty much you can find everything in terms of repositories and code to get you going. Quick start sample apps and the like, all at github.com/Yugabyte. Yeah, that's going to be the place for you to go. So some very helpful links as we start for our session today. All right, cool. Okay, so for this course, it says intermediate, but it's really for the whole course here. We're going to be talking about really Ysql as a language, constraints, UDFs, indexes, views, triggers, extensions. What's missing from here is probably the advanced topic. My apologies, but we have things like stored procedures and things like table spaces and geo-partitioning of data. I'll cover in today's session as well. So I already mentioned signing up for YugabyteDB Manage. That's the good news. Once again, you can go to cloud.yugabyte.com and you're ready to go. Okay, cool. So what is YugabyteDB? YugabyteDB is a distributed SQL database. And if you're part of the Distributed SQL Summit joining us today, probably have that curiosity. What does that mean? In many ways, it means being a geo-distributed database, like this map indicates, right? So for those of us who've built these types of distributed systems, we know that the database can be a real bottleneck, the traditional monolithic database, right? Because it's located in one region, in one data center. And to try to build distributed systems or microservices or cloud-native applications on top of a monolithic database can be really challenging. You end up with doing things like, oh, we're going to manually shard data. So now we have different servers with different shards, or we're going to use read replicas, and we'll have write patterns and read patterns and all these things. It can get overly complex very quickly. But with the database like YugabyteDB, you can have a distributed SQL database that is geo-distributed, and you'll see in my example today, even on running on a local machine, how we can mimic that. You'll want full, as a database, you'll want full distributed ACID transactions. things like that. You'll want some APIs that are compatible with existing databases that are out there. So, for example, YugabyteDB supports 2 APIs, one for structured query language, which is PostgreSQL, and the other is similar to a structured query language, which is Cassandra compatible, which we call Ysql. Mark gave that presentation earlier today. And of course, you want it to be open source, right? So that you can get started in your organization, in your enterprise. So that essentially, in a nutshell, is what YugabyteDB is. And there are really 5 characteristics that we think are very critical for describing what distributed SQL is. There are a bunch of other vendors out there and GitHub projects, open source projects that claim to be distributed SQL, but they probably don't meet these types of characteristics. Like, oh, yeah, we have a MySQL API, okay, but we don't support foreign key constraints. Oh, okay, there we go. Like, really quickly, you get a degree of wire compatibility, but not language compatibility. So first and foremost, you really want an SQL API that's highly compatible with an existing open source database, for example, like Postgres Sql. And that's what YugabyteDB offers. The other thing is you want distributed data storage. So what that means is that every node in quote unquote a cluster essentially has the ability to store data. So it's not an AWS S3 bucket that every node needs to access. Not that that's bad, it's just, but that's not really distributed in nature. It's stuck to a specific region and so on. And talking about replication of data, that's critical for fault tolerance. And so a lot of distributed SQL databases that might be out there will asynchronously replicate data. Like they might have only the ability to just support an active to passive replication or unidirectional replication that's asynchronous in manner. But what you really want is a synchronous replication of data. And the ideal part of that is that you just don't have to worry about any replication lag for your workloads. And every other node, I would say every node in your cluster, because a node represents compute, memory, disk, and network, should be able to process a query. There are a lot of distributed quote unquote SQL databases out there that have differentiations between, very much like Spark SQL, like who's a master node and who's a worker node. So you have to direct traffic accordingly. But what you want really is to maximize the use of that commodity hardware, whether it's bare metal or it's virtualized, either one, it doesn't really matter. All of them should be able to accept a query and process a query. And that query needs to be able to be distributed in nature. A lot of that has to do with how your data is being stored amongst in the system, whether that's sharded, partitioned, or the like. But your query should be able to access all the data storage, so to speak, in a distributed manner from any one of the nodes in the cluster. And, and speaking of sort of query execution, any type of transaction that exists for a node that has a client connection also needs to be distributed and needs to be fully ACID compliant, meaning atomicity, consistency, isolation, and durability of the transaction. So we don't want to be in a situation where your distributed SQL database is just eventually consistent, so to speak. That would really undermine the whole purpose of a transactional database in that regard. So with YugabyteDB's architecture, what's very unique about us, and if you're in Mark's presentation, saw a similar slide, is that we have YugabyteDB and we have really 2 different sort of layers in the architecture of the database, right? There's a query layer, which allows for multiple APIs. And at one point in time, we had a Redis API that's been done. But with Cassandra, Ysql is one, or we have one that's a Postgres Sql, and we can connect to it with a Ysql. In the query layer is very powerful in the sense that it can accept any node in a cluster can basically access that And in terms of distributed storage, that's the other part of the architecture. And the way we store data is in a customized version of RocksDB, which we refer to holistically as DocDB. And that's going to be in charge of sharding and load balancing in terms of like data distribution and making sure the data is most evenly distributed as possible amongst the nodes in the cluster with storage, which they all have. It's going to also be responsible for strongly consistent replications, right? Synchronous replication. And it's going to be also in charge of how distributed transactions are being managed. Something you certainly don't want to build if you're manually sharding databases. And then multi-version concurrency control. So that's in a nutshell, a very high level, what YugabyteDB's architecture is about. Yeah, so in terms of what we're going to cover in our short time together today, in terms of Ysql, things that you should know from a high level and take away is that it's a Postgres compatible API. And currently we're at version 11. So I know on a roadmap we have support slated for Postgres 13, but I don't know when that will be coming. If I was to speculate, which I'll do right now, that probably would be by the end of the year with either 2.16 or 17 or something. And in terms of what we do very well, we're a relational database management system and if you need ultra resilience, massive writes, scalability, and you need to be able to, for compliance reasons or just the applications you're trying to build, trying to ensure that you have geographic data distribution so that quote unquote you're on the edge, closer to the user, we're ideal for that. And if you don't want to give up everything that Postgres embodies in terms of almost 50 years of SQL advancements, such as support for foreign keys, joins, distributed transactions like partial indices, triggers, and so like, then we're a great choice, right? Because we support all those things. And here it says serializable and snapshot, but we also have a third form of isolation recommitted that's also been added. And then very much like Google Spanner, we're what we call CP, consistent and partition tolerant. Yeah, everything will be available, as I mentioned, in our course player, as well as the recording. You'll also have the recording available at distributedsql.org. Cool. So when we're talking about the differences between YugabyteDB and a Postgres SQL database, so first and foremost, Postgres is an awesome standalone database, right? And it's been it's been tested and proven in production environments around the world. And it does what it does very well. So when a client connects to a Postgres SQL database, Postgres SQL has its own query layer that's going to parse, analyze, plan, execute. I forget what the thread is. It's called PG backend or the processor. And then it has its own Postgres SQL storage layer and a write-ahead log and so forth, and it persists data to the disk. And that's excellent. The situation is when you run out of capacity in your Postgres database, like you can't just size up anymore in terms of hardware or disk. There are only so many connections, even with a very massive, expensive $250,000 a year server that you're going to be able to manage. So you basically, it's like a refrigerator that you have. Or a freezer. There's only so much that can go into it. And then you need to get another one. But then you have two different things, and how do they talk to each other? That's the real challenge. So that's like a single node Postgres SQL cluster. What we do in terms of that YugabyteDB architecture, when we create a cluster, right, we reuse that Postgres SQL layer. And that's really where a lot of our magic comes into play. So we just enhance that Postgres SQL layer and then do our rewrites for a customized document store, which is called doc. So a client can talk to any one of the nodes in the clusters, and to the client, it's basically saying, hey, I'm using a Postgres SQL. For example, I was showing JDBC driver for Java application. And behind the scenes, what we're doing is we're just reusing that Postgres SQL layer. It's customized for Ysql. And then we're just storing data and retrieving data from a docdb, which is a key value rocksdb store, right? And those enhancements to the PostgreSQL layer within YSQL basically fall into these three types of categories. They're like table statistics or geographic location-based hints, or just rewriting the query plan for distributed SQL and making sure we're doing things like pushing down things to docdb. So when we compare those two, like YugabyteDB and PostgreSQL, both of them, of course, have an SQL API. But when we get into things like distributed storage, when you want to horizontally scale or scale out, when you want to go from 100 gigs or a terabyte of data to 10 terabytes of data or 100 terabytes of data, that's where PostgreSQL is the road ends, and there's just a cliff. But with YugabyteDB, things like distributed data storage or replication or distributed query execution and distributed asset transactions, they're all built in. You don't have to think about it. All you have to think about is, oh, just point my app to this, and essentially the app's going to run thinking that this is PostgreSQL. Now, there certainly is an asterisk next to that, right there, and we'll talk about that in today's course. There's a lot of sort of language features that we don't support, and then things that are customized. So I would say generally highly compatible is the term I would use. The things that are customized, like PostgreSQL extensions, like a lot of those things are very dependent on how PostgreSQL stores data in its own storage layer. And so we just haven't, I'll give a couple examples, but we haven't rewritten that layer. And then there's some other sort of technical database internals like bitmap indexes that we're not using that PostgreSQL does. Will those things change? Most likely, right? As our product evolves and catches up to the most recent version of Postgres. Cool. So when we're talking about compatibility, like a lot of the languages, the terms and things and so forth that you'll see here, and I already mentioned like the asterisk, like things with extensions and so forth. We all in support a couple that will, or that we've ported that will work with our distributed doc store. And there are like hundreds, if not thousands of those things. I talked to you a little bit about installing locally and using multi-node cluster or using the fully managed cloud signup. So I'll just skip over this here. And then there are third-party tools that you may want to use, like pgadmin, PostgreSQL admin. If you're on a Windows machine, there are a couple of little bugs just with pgadmin and Postgres. With character sets, and you can just Slack. If you run into any of those, you can just, not Slack, but you can just search on Google and like Stack Overflow. We'll show how to resolve some of those things pretty easily. They're very specific to a Windows installation. But that all said, those tools like pgadmin will work just fine. Connecting either to YugabyteDB managed or managed service, database as a service in the cloud, or if you're deploying to your own environment, or if you're just running locally, you can use a tool like pgadmin, dbbeaver, whatever it might be. Anything that will accept that JDBC type connection will work fine. So anyhow, okay. And if you want to install a sample database, you can do that. For example, we have a Northwind sample database. And some of these slides will use those connections and so forth. But I'm actually going to jump over here to a demo to show you how that kind of runs. And we'll make this environment available to you just as a Gitpod environment. And you'll find that link in the course player later today. I just wasn't able to get it up and running this morning, unfortunately. So you should be able to see my screen. Yay, you can. And I'll make this a little bit bigger. And we'll get you set up in this type of thing in just a moment. But essentially, for our demos and a lot of our hands-on labs that have to do with working with YSQL or YCQL, we know developers like to use, and administrators and operators now, because everybody's working as DevOps, SIP-stops, whatever it might be, basically working in under continuous integration and continuous delivery, right? It's just a matter of corporate policy. So everything is managed code. And what that means is typically that we're working with some type of IDE, integrated developer environment, whether we want to or not. And the nice thing is I have VS Code here, but I can deploy all this to a Git pod for you, and you can run it up in a Git pod environment for your cost. All you need is a Hub account or Bitbucket account, whatever it is, and you'll be up and running. And they'll give you basically an Ubuntu VM with 12 gigs RAM and 4 vCPU, enough, just like my Mac, to get things up and running. So there's pretty much no difference. And you can run, instead of VS Code locally, you certainly can pull the repository and do that. This is a notebook that's in Jupyter format, and I have a repository here for today's session. And we'll just run through the notebook. We have a bunch of data files that we'll use, some utility functions, and so on and so forth. This is a matter of convenience. You're most certainly welcome to look at any of these and modify them as you see fit and so forth. But I'm just running a couple of things to prep these environmental variables that I have, things like paths and so on and so forth. And all of that will be stored as notebook variables, and I can share these between notebooks by calling them back. And then for a local installation that I have on my Mac, what I need to do is make sure I have a couple of loopback addresses, because what I'm going to do is very quickly just show you how I can spin up a 3-node cluster on a local machine using a command line tool that we have if you download YugabyteDB called YBCTL. And it's only used for a local machine. If you're doing it in another manner, you can use YugabyteD and basically do the same thing, whether that's on a local machine or as a distributed system using the YugabyteDB core, which is an open source version. That's what I'm using here. So that's what these loopback addresses saying, that if I'm on 02 or 03, I'm running a process on that that's bound to that, it will loop back to 01, and those systems won't be aware of it. So the next thing I'm going to do here in this bash command, let me just go full there, that you can take a look, is I am going to run, as I mentioned, this YBCTL, and I'm going to create a cluster with replication factor of 3. That's important for Yugabyte, because what that means is I have data that's going to be, one is can be strongly consistent, but it also means for this command line tool, I'm going to get 3 nodes. And I have a couple of different settings here for 2 different processes that we have. We have something called a tablet server, T-server process, and we have also a master server process. The master server is in charge of like the system catalog and the like. But the tablet servers, they're in charge of really how data is stored, and also in charge of how client, like the query layer too. So they embody both. And we have a number of shards per T server set as 1. And the reason why I'm doing that for this is to demonstrate that a table is going to basically end up being distributed storage. So we're going to shard that data, and I won't go into those details in this course. But we're going to shard a table into what's known as tablets. And we typically do that using one of the 2 sharding algorithms. One is consistent hash sharding, the other one is range. And it's very dependent on the number of nodes that we have, in this case, in the cluster, at least when we start off here. This YBCTL replication factor of 3 is going to say for every table, or I should say in this case, every tablet, in fact, I'll have 1 leader and 2 followers, so to speak. But at the very minimum, I'll need 3 nodes because I'm having a replication factor of 3. So long story short is each node for any given table will have 1 tablet shard on it. So if I have 3 nodes in my cluster, I create a table called table A. I'll have a tablet 1, a tablet 2, and a tablet 3 for table A, 1 in each node of the clusters. And we can have some placement info for a geo-distributed database. Now, arbitrarily, what I'm highlighting here is that placement info for the tablets per, well, in this case, per the nodes and where the tablets would go. So I'm just calling it Cloud 1, Region 1, Zone 1, Cloud 2, Region 2, Zone 2, Cloud 3, Region 3, Zone 3. But that could be Azure, and whatever region Azure is in, and within that region, a specific zone or data center. It could also be with Azure, it could be AWS, right? The same thing, US East or whatever, in a certain availability zone. And then I could have Google Cloud. So I could actually have multiple cloud providers here. So this is an arbitrary setting. Behind the scenes, you have to make those VPCs in the, but it could be a single cloud provider or multiple cloud providers. It could be a single cloud provider, one region in multiple zones, or multiple regions and zones. So this is totally configurable. So anyhow, I'm just going to get this thing up and running. Stop talking. And what we'll see pretty quickly is I probably had something already existing. I'm going to destroy it, and we'll get it up and going. We'll take a couple of seconds, I hope, on my local machine. And I'll see if there are any things here. Any questions? Cool. So here you can see part of my install, I have a Ysql shell, a Ysql shell. Yeah, this is deprecated. But you can see I have 3 nodes with a replication factor 3, so it did all that work for me. And basically saying, hey, if you want to connect using JDBC, for example, hey, you can use this Postgres JDBC, use Postgres SQL, and connect to our default port 5433, and our default database is Yugabyte. So all that information is there. So that means this is up and essentially up and running as my standalone. So I have a couple of things that I want to do here. Let me clear this in terms of getting some things up and running here. So I'm going to get some environmental variables set up, and I want to create a database called DBUYB, which is going to be a default database that I have here. I'm using bash to run these commands, and mostly just because I want to run, this is implementation of the Jupyter Notebook implementation that we have, but we can have different languages, Python, Bash, SQL, Magic, SQL through this interface, so it's pretty handy. But these Postgres commands like /c or /l unfortunately aren't easily managed by SQL Magic or cell in a notebook called an SQL cell. So that's why I'm running it in Bash, so we can get that output. And you can see here I have my new database, DB, and I'll create some utils that I just have. I may or not use, and these are basically there's another Bash script just saying, hey, you have some folder files that are in these folders, and we want to basically connect to this database, and I want to execute this file. So I'm going to create some functions, for example, or if I have some internal metrics that I want to run, and so on and so forth. Okay, cool. So that will get me going and up and running for what I want to, at least what I want to do initially here. And so I have a system that we can run. And if I wanted to run some other scripts that I have here for different data files, like want to load some world data, I can do that. This may or may not work. And then table countries and do some record counts. So I just want to show that this is working, and then I'll jump back to my slides. Yeah, let me take a look and see if there are any questions. Cool. Yeah, we'll make this available in our repository that we have for the university, and you'll be able to just hit a button and go to Gitpod, and we'll just start up magically for you, and you can go through the notebook just like I am doing, just running line by line by line. Yeah, this world cities data is pretty large. I think they're like at least a couple 100,000, if not a million cities and so forth. So anyhow, here are the list of sort of the objects that I have in the database YB. And here's a description, for example, of table countries. Yeah, but you can see these are all things that we're familiar with Postgres SQL, the interconnect data types and the like. And then I can connect to this database. In this case, I'm going to use Python to connect to this. And then our notebooks use, as I mentioned, this IPython extension for Jupyter Notebooks. And it's called the Magic SQL. And this is all I need to do to basically say, hey, let's connect here using this connection string that we have in place here. And there is a Python driver for YugabyteDB. I just haven't tested it. So I have some notes on that, but I think we can use it as well. My recollection is we can, we just haven't put it in. But I could be mistaken. And anyhow, this will give the final counts for the rows of data. Okay, cool. So let me jump back then. Let me jump back to our slides that we had. Let me see if I can get that up here. There we go. Perfect. Talking about YSQL and as a language, and I'll give some examples too. I just want to get them. Many of us are already familiar with the primary key, what it is. Essentially, a way for us to identify a row uniquely in a table, though in many cases, or by design, by making sure that row is unique by that ID, and you typically can only have one primary key. And this is an example of the Northwind database, like the entity relationship diagram. So a table like customers will have a customer ID as a primary key, meaning you can have a customer with an ID of 1. No other customer can have an ID of 1 in that case. So just like you would do that in PostgreSQL, you do the same thing in YSQL. And that's really the moral of the story here. So we have a create table, which is a data definition language statement. And we have here a primary key on category ID. Right? So if I create this table that we have here, and I look at the description of it, we'll see here the primary key. Now, the thing that we have here that's of interest to us, and we have other courses that will go into this at the university, but you'll notice here, we do not use a B tree index. We use what's known as LSM, or log structured merge tree index. And that has a lot to do with DocDB. But, and then in addition to that, you'll see our indexing strategy for us is really our sharding strategy, which in this case by default is hash, right? So what that means is that we're using consistent hash sharding for this table. And internally, what that's going to mean is that this table categories and category ID in particular, the values will go through a consistent hash algorithm, and they'll be assigned some hexadecimal value. But internally, that range is like 0 to 65,535. And our partitions in our what should say, our tablets for a given table will essentially show what those partition ranges are, what that range of values is, the beginning or the middle. So if it's 3 tablets per table, and my cluster, like for example, that I created, will essentially have values that will be stored somewhere between 0 and 21,000, and then 21,000 something to 40 something, 40,000, and 40,000 to 63,535. And we have some functions beyond the scope of this course that will show that, like YB hash, for example, will show the integer value. But that's what's happening here with our primary key. So, but under the hood, it's working with our document DB store. And it should be mentioned that each tablet that we have is essentially its own RocksDB database, right? Customized version of RocksDB. So you can have thousands and thousands of tablets in a YugabyteDB cluster, right, representing hundreds of tables, but each one of those tablets is its own customized version of RocksDB, and they, because we're using replication factor 3, they're forming their own sort of group tables. Yeah, or what we call a RAF consensus group of tablets, where we have a leader and followers. Now, for us, for folks who are just writing YSQL, then I have a composite key, primary key columns, and you certainly could use something like that. So again, category ID in this case, and then we have, and then you can certainly support foreign keys, right? If you want to define a relationship with another table and make it as part of that constraint, for you can do that as well. So it's simply just saying, hey, I want to define a foreign key, reference this other table, for example, called region, here in the table territories, like this, just like you would in Postgres SQL. And as you'd expect, we will support things like those cascading delete and update, right, for referential integrity. That's not being sacrificed. So if you do something like an on-delete action, you can do that. Cascade is probably the most popular, so delete's all referencing the rows in the child table when the rows in the parents are deleted. Also be deleted. You need to implement something like a check constraint of do the values get stored within a certain range, you can do that as well. Cool. And then you can have unique constraints, right? So if I want like a username or an email to be unique, that's certainly supported as it is in Postgres and MySQL. And then also for your column definitions, you can use not null as well as a part of the column definition type as part of the constraint. So I'll jump back over real quick here to the beginning of the other things that I have here. Really my first lap. So I want to show here as I'm connecting back to this database that I created, YBU. And then let me see if we can get this working. Cool. There's some internal statements and prepared statements that I've created. So let's take an example here where I create a table called table departments and a table called table employees. So I have both of these in this case, table departments and table employees. And so the things that we've talked about, like constraints are here, right? I have a primary key. And now I'm not even describing it like saying use hash or anything like that. All of this will be interpreted by Ysql accordingly, and so on. So we can look at the table descriptions in just a moment. So I'm going to create those two tables, and I'll insert some rows into those tables for table departments and then table employees, just a handful of rows and so forth. Now, if I want to look at those tables on my local machine, I certainly can do so. So let me jump over here, back to this, and let me just jump real quick, and let's see if I can look at running locally. So I have this 3-node cluster that I created in my notebook, and I am on one of the hosts on port 7000. And this is basically one of the master services that's running. But you'll see that I have another 2 master services that are running on O2 and O3. And the replication factor sets the number of masters that I'm going to have. Regardless, these guys have their own sort of graph consensus group, but one of these is the leader and the others are followers. And it doesn't really matter which one I'm on in this case. But let's take a look at our tables, because that's what I just created 2 new tables. And one called departments and the other called employees. So here are the 2 tables that I recently created, and I'll go to table employees. And the first thing that you should notice is because I created this cluster using these placement groups, you'll see that this table actually has 3 replicas, and there are 3 different placement blocks. So that will make sense in just a moment. So they're basically 3 different, essentially, blocks where table shards will go, which we call tablets, right? One will go into this block, one will go into that block, and that will go block. And Yugabyte will just take care of that for us. So that's the good news for us. And we'll see here, we have all the columns that have been defined. And this is being called a partition key. Another way to think about it is a shard key. But basically, this is how data is going to be distributed based off of the definition of the employees table, which by default was hash sharding that we have here. So because I have one node, I have 3 nodes, and by default a configuration of basically one shard per node per tablet for a given table. That's what we're seeing here. So I have 3 tablets, 1, 2, 3 for this table employees. And each one of these is going to be assigned to one of these regions, as if I could look at it. And then this hash value basically represents the very beginning. This is from 0, and then up here is 65,535. So you have 3 sort of groups of buckets where rows will live based off of that consistent hash sharding. In each one of these tablets with replication factor 3, we have one of them is going to be a leader. And then for this leader, there'll be 2 followers on the other nodes in the cluster, right? One on O1 and one on O3. This tablet, its leaders on O1, it has followers on O3 and O2. This tablet here, ABE, and ending in 85 is unique ID. Its leader is on 03 and it's two columns here. So the host that I'm on is 127.00.1. This is where my leader is. This guy, this tablet here is living there. And so it is. And you can actually go and go to those tablets and look at those tablets on a tablet server, right? So on O2 here on this individual tablet server, and you'll see that here are my tablets, and each one of them will belong to one of these clouds and regions that we have specified here. I'm running on a different port by default. It's usually 9000 because Jupyter Notebooks run on 9000. We have it assigned to 8200. So if you're just questioning, but if I go to this specific tablet server on 8200 and go to the tablet, I should be able to find here this value for this tablet right here, and here it is, this table employees, this is the leader, and so here's the given tablet that I have, right? This is where it's living. This is the tablet ID, and it lives on this host. Okay, so that's about as much detail as I want to jump into there. So on and so forth. Okay, cool. All right, yeah, let's go back over to some of our slides real quick, and we'll wrap up in the next. Yeah. Other things like functions, expressions, operators, all supported YSQL, right? So if I want to do things like I want to create a user-defined function, I can do that. Count of rows over a table, no problem. So for example, if I want to count those rows, have a shorthand function that does that, I can do that pretty easily. Function parameter modes and PostgreSQL supported in YSQL. So things like in and out, fully supported with your functions. So you can have the out function parameter. For example, in this example, we have min, max, average price, and so forth. That will give that quote unquote record of that. I can set it as a record if I want to be more specific. And then you can do things like you expect to do, like function overloading. So that means I can have essentially the same function, but with different number of arguments in this case. So I could have count of products with an argument for a product ID. But I could have another, the same function called count products, but it's overloaded as product ID and the discount value. So you can use those types of language features in YSQL as you can. And here's an example of running both of those. Built-in functions for aggregations are all supported, like average, count, max, min, and sum. Date functions are supported, right? So these are all PostgreSQL functions essentially. And there are, whenever you're dealing with like dates in particular, there are a lot of nuances. We have some great blogs on those nuances from some of our SQL or PostgreSQL experts like Bryn, for example. It's great blogs on date functions and date time parts and the like. For even Postgres or MySQL folks to really nerd out. So if you want to do something like age, right, of an order, you can do something like that between two dates, or age with the current date, pretty straightforward in this example, age, current date, max, order date. String functions for manipulating character data, whether it's ASCII or trimming something or using an MD5 type algorithm, or looking at the position of something, or repeating or replacing, reversing, or putting things upper or lower. So if you want to concat two strings, you can do that. You concat and make it lower. You can do something like that. No problems. Or if you want to left a certain number of characters, you can do that as well, and so on. Math functions, tons of math functions in PostgreSQL. If they're in the 11, we're pretty much bringing them over. Here's just a handful of what those supported functions are. So if you want to round numbers, you certainly could do that for unit price. Or if you want to in this case, use a rounding a random number multiplied by some value, you can do that as well. In this case, I'm trying to concatenate some type of random email for a user. And then if you write a lot of SQL at a certain point in time, especially for, I would say for online analytical processing or OLAP, like answering business questions, one way to put it, you'll have some window functions. Yeah, so we'll support those as well. Things like average, min, sum, count. These all have an asterisk next to them because they're basically they're overloaded functions, right? Used for both aggregations and windows. If it makes any sense. But things like dense rank or first value, last value, or entile, rank, row number, lag, all those are supported. Here's an average, and you're just using window function over partition by is usually the syntax that you would use in your select command for things like that. And here's an example of rating, I should say ranking products in this case, by unit price in this case. And then other types of expressions besides functions that you could use, whether they're conditional expressions in your select clauses like cases or coalesce or null, if, or casting between one type into another. So all of that's fully supported. Here's an example of using your case logic. Especially helpful if you don't want to do a lot of if then and so forth. Okay, so I'm gonna jump back over real quickly to the essentially my notebook that I have. And let's take a look at some of the other things that we can do. So of course you can use Ysql to update, access, and analyze data. So these are DML statements, moving from DDL statements. But so for example, if I want to update a table, I could do something like that, no problem. And then if you're familiar with PostgreSQL, like they're, especially for application developers, rather than having two commands, one to do the update and then another to run a select, you can do both in PostgreSQL. So that's a nice bit of syntax sugar. And here's an example of that. So we're updating the salaries, everybody gets raised except managers. And then we return who those folks are based off of the employee name and salary. So with one command, you can get both from, and so we'll support that as too. An update and select statement. So that's going to be really helpful for applications. Here's a scenario where I want to join, no problem, on table employees. And if you're looking at this, the join is between the table employees and it's an inner join, as you can see here, on itself. So this is a self join. So a self join is fully supported, for example, in this case, they're showing. You can do things like having a prepared statement. Unfortunately, the notebook and sort of the notebook cells don't quite always support all types of syntaxes. So typically I have to wrap this thing in some type of DDL file, and then I'll be able to execute it as the function that executes the dynamic sequence to get around it. I won't run it here, but essentially you could do something like do this statement for a prepared statement. And a prepared statement is essentially will work in the context of the client connection, right? So I am connected to my local database through this application called this Jupyter Notebook through these individual cells. And in fact, this is this SQL cell that's using that Python connection string. So that's a connection in itself. But if I run a bash cell, that's through the Ysql command line, Ysql shell command line, that would make a different connection. So that one would not have access to this prepared statement. Let me put it that way. Only these SQL magic cells will have access to that statement. So I don't know if this is going to give me a result, but whatever. But that would be the example of executing something like this. So anyhow, we'll come over to indexes in just a moment. Just give you an idea of how some of that's working. Okay, great. Let me pause, see if there are any questions. Cool. Yeah, indexes, we support them. We again are using our log, basically the main takeaway is indexes in YugabyteDB are distributed just like tables are distributed into tablets. So they get sharded too. And in fact, an index, it has the same type of sharding strategy, right? So it's either going to be consistent hash sharding or ranged. It's the same as what you would do for a table. So indexes are distributed, and that's an important thing to understand, right? We'll support unique indexes. We'll have an include. So if you want to have a covering index, so your query's covered, you can do something like that. You can use where clause in your index and so forth and so on. And then we also support things like generally inverted indexes, so a gin index, but that's a little bit beyond the scope of this course. But they're also in support. So for example, if I want to make unique with a hash column ordering, I can do something like that. That would be these here, just index on products, product SKU, and this would be the default. And what we would see is that's a distributed index, just like we saw for a table. It will have 3 different tablets based off of our local cluster configuration that I have on my Mac machine. And you can have an ordered index, right? So in this case, you can say, oh, I want this here, product name, to be ordered in this regard. And it actually, that's a little bit different, right? Because in this case, I'm not using hash, but the default will be range. In a range sharding strategy basically means one tablet at the very beginning will basically have all the values within the range. And that really has to do with tablet splitting size. But once it hits its upper limits, maybe it's 1 million rows, maybe it's 10 million rows, depending on your cluster configuration, it will split into another tablet to represent another range. So these indexes are particularly important, especially if you have a query like I want to do between two values, between 100 and 20 million or something, or more likely between 100 and 200, but I got 200 million rows. Those types of range indexes and having it within the range sharding strategy is ideal, much better than the hash shard. And you can see that in the explain plans, and we'll look at a couple of those. So you can also have an include, right? So in this case, on products, I want to include the product SKU. So if I know I have a lot of queries, I can have a product name and product SKU. I can take advantage of doing something like that. And essentially that will mean is we'll use the index only in the explain plan. We won't have to, and what that means is we'll just use the index tablet that's associated with the product name and that also has the column product SKU in it, if that's what my query is. Select product name, product SKU from the table products, where product name equals Yugabyte, for example. And that's ideal, because then we're going to get a faster, high-performing query in that regard. And then you can even do things because tablet indexes are tablets, you can do things like you can split an index into multiple tablets. You can do this also with a table, but it's also supported. You can use that split in clause. That's more of an advanced tactic, but that's certainly possible to do as well. Partial indexes are great when you have a subset of a table that you want to use. So for example, like with the Northwinders database, you have an orders table and a ship date, but the queries that you probably have, right, either care about things that have shipped or not shipped, right? So in this case, we're saying where the ship date is null, meaning that hasn't shipped. So I don't want to see any of the rows that have shipped because we don't care. We want to look at the stuff that hasn't shipped. But you can use those partial indexes as well for that. And then index backfills. So there are ways to basically have a backfill being supported non-concurrently or concurrently. That's a little bit beyond the scope of this course, but we do have a bunch of flags and settings that are available to configure the behavior of your YugabyteDB cluster. Yeah, and here's an example like Ysql disable index backfill to false, right, when starting these Yugabyte servers. We call them global flags, and they can be put in a config file, or they can be passed in as parameters when they're started, and so forth and so on. And there are a lot of them. For those who are curious, just like how many there are of these, you can look under utilities. So this is for my tablet server here, but you'll see we have a bunch of flags that we have here that are associated. So there are lots of flags that you can pass in. Some are for YSQL, some are for YSQL, and so on and so forth. So we were talking about index here. Backfill index client or disable index backfill will be listed here. If you really want to start diving in, it's a great place to get a local install or something like this. And you can start looking at things like all the different global flags are cool. All right, so let me jump back in. Thank you. Okay. And then not supported, like using or guest indexes or brand or collate, and not applicable or B-tree for us. So here, let's take a quick look at some of the examples. I'm going to create a table called table demo. And then in this one, we're going to just create here. I generated some values here, like 42 rows, and we'll create an index for them. So let's take a look real quick then back again. Go back here. And then let me see if I can get this out to our to this host. So let me go back. Go back to the tablet server, go back to tables, and we have user tables. This is for the master server, excuse me. Back to the index tables, and here's my index called index demo val that I just created. Again, just like we saw on the tablet, it has these 3 different placements, and then notice it had here, it's a tablet itself. This is an internal ID that you don't have to worry about. Basically, that's the pointer back to the existing table that this index is based off of that we have. And then we have, you'll see this again, it's using hash splits and so on and so forth. So based off of these values will be based off of range will exist in one of these tablets, the 1 through 42 values. Okay, yeah, so I created the table, created the index, right? And you can, if you want to improve, you can run things like analyze and so forth to get better statistics about the table. And then here, I'll run this. And if you want to see what the explain is for this, here you'll see the execution for this explain. Select from table demo where this value is and so forth. So this will give you an example of how this is running. Explain plans are inverted, right? So you basically would start down here and then go up. But this is the line that we care about. You can see here we're using only the index itself on index demo in this case to find it. And if I have some time, I'll show some of our utility functions that we added so we can actually see how this data gets accessed at the lower level within DocDB. We've put in some of those utility functions to show that. I just didn't include this in this demo. So if I have time at the end of this presentation, we'll go through that and so on. So anyhow, I want to talk about some built-in functions that we saw earlier that I skipped over, like, for example, Windows functions. Yeah, we can do that as well, just to let you know. In this case, we have lag based off of the hire date, the time, and so forth for the different users, how many days they were hired after somebody else. We could do that. Other expressions that we could use, like here's an example, regex within the predicate, the where clause. And we're searching for emails basically on these type of values, who has an org or a Gmail account or something like that. Yeah, here's something like a CTE, and I think we'll get to this in just a moment, but common table expressions are fully supported, for the most part are fully supported that we have. So here's one, it's going to be a CTE for an employee's evaluation period that we're using here. So we can use something like that. And other sort of supported functions that you could use, this is a command called the Crosstab View. I can't get this one. I'm sure there's a way to do it, to get it to work, but I haven't figured it out. But essentially this would be this type of command. And you can certainly just open up the shell if you're in Gitpod on your local machine and just use Ysql and then execute, just use that quote unquote Ysql shell. And then this command will work. It's just not working in the SQL view itself. And here's an example of an entile function that we have. Yeah, used within CTE. Okay, cool. All right, let me jump back over real quick then to back to my presentation. Okay. All right. Things like views also supported. So you can create a view. It's a nice way to, if you want to use something like column level security, you can use like views and just give access to a user, i.e. a role, to a specific view. That's a pretty typical way of doing things. Or if you have a specific condition in place, a lot of folks encapsulate their complex select queries into views just because it's a nice way to encapsulate that logic, but not everybody. You can make views as an updatable view. That's certainly supported too. Here's an example where we're inserting rows into the view itself as well. Now, most folks look at a relational database management system and they expect many of these sort of advanced features, such as triggers and stored procedures. And there are a lot of vendors out there who go, that stuff doesn't matter. Just do it in the application. as a system of record, you really want your database, and especially your distributed SQL database, to enforce referential integrity. And in certain cases, it's much better able to implement, because it can do it in a transactional manner, business logic. And there's arguments about whether you should put that logic within like a business application layer and the application layer all the time. But the reality is, in distributed systems, sometimes if your database can do it, probably the best place to do it, because it's just going to have those ACID type properties. Anyhow, that's certainly true with distributed SQL and YugabyteDB for triggers. So here's an example where we'll have a table called customer audits. And the goal is here, we want to put some type of trigger on here. Like somebody, like the goal is like, let's write to this data, this table, this audits table, when somebody messes around with the customers table, whether it's an application or individual user or whatever. So we could do something like this. Oh, let's log any name changes to this table. So here's an example of creating a trigger using PL, PostgreSQL as the language. So we have a new contact name doesn't equal the old contact name. Then we're just going to insert a row into customer audit. And then we create, so that's the user-defined function. And then we create the trigger itself called contact name changes. And then we define its behavior before or the update occurs. It could be after the update, but before it does, before something goes through customers for each row, let's execute that procedure, the user-defined function called log name changes. And so, anyhow, that's, I'll get that. I think I have an example of a trigger here, but we'll see when I get to an advanced feature. I might have an example. Sorry about that. Jump the gun. Yeah. And so when we updated these customer contacts, you'll see in customer audits, these cases we're recording what those changes were, what the contacts were, and so forth. So you can do that. The other thing for those in particular are concerned about Postgres, right? And they want to have things like, it's important to have things like extensions. We have a handful of extensions that we support within Yugabyte. Mostly, as I mentioned earlier, like the limitation for us is a lot of extensions, besides being written in a variety of languages, are very specific to how Postgres stores data in its storage layer, using its raw files and the like. So there's an extensions folder you can take a look at. Like this is typically what folks would see in a Postgres stuff, like anyhow. But we have a bunch of pre-bundled extensions in a Postgres directory that you'd have. So things like fuzzy string match. If you want to use that extension, all you do is say create extension fuzzy string match, and then you can have that soundx type operator in your predicate filter expression that you have here. So soundx contact name sounds like Peter Frank, and you get these types of results. A lot of folks want to use PG crypto. Basically, in this case, they want to have those cryptographic functions like that you list here, MD5 or SHA or like whatever they might be. So in this example, you're encrypting a password and you're adding a salt to the hash, essentially, in this regard, and that would be your result. So you can do that as well. Okay. All right. So I'm going to take a look at sort of some of these other advanced features that we have here. For example, like using GIN as an index is certainly, that's a generally inverted index, is something that we support here as well. So I can run this. Let's see if this works. Yeah. And then with that GIN index, I'd be able to, in this case, for the employees table, we got an example of doing this earlier with JSON, but I could use that type of expression with GIN and this type of GIN operator in this case to support that GIN index. And if I look at the explain on this, you'll see something I'm using the index scan, and I'm supporting that query on the JSON-B data type. And like those types of extensions like GIN and the like are for these advanced scenarios. They can be really helpful. If I want to do something internally, we call it YBGIN. So that's why I'm calling it this way. But here, for example, if like I want to do some type of use the 2TS vector expression, like it's basically the similarity. In this case, it's like extracting a list of words that can be compared, like every from description. That's what it's going to do here. And then when I take a look here and look at simple, responsible, and services, I'll take advantage and I'll use that index here. And you'll see it's saying using the index scan using index YBGN in this case. So you can implement those types of things and get them out. The other thing is, just like triggers, we have things like stored procedures. So here's an example, stored procedures. This one is going to be on a procedure where we're going to have commissions transferred between one employee and the other, and we'll raise some exceptions if they don't go through. So here, these are the two employees, and we'll say, hey, one of these employees is going to get $200 from the other one. So we'll give that a go here. And we'll see what this is, where the commission's not null. So these two employees are 7521 and 764 that we have here. You can see the commission, 1600 and so forth. So we'll go 752, and we'll give it another 100, and then we'll run this again. And that's all being done through a stored procedure in a transactional manner. And if I exceed that amount, we should raise that exception, as you'll see here. Oop, there's a raise. And I don't get the full list here, but I did get the cannot transfer that 1,000. They don't have that from 752. It just doesn't have that amount based off of that, and so forth. And then we were talking about triggers earlier. Here's simple. I can add table departments, like a last update here for table triggers. So I added a new column to it, and then I'll have a function called department last update. That's my function that I'm going to use for my trigger. And then very simply, I'll just create a trigger on table departments, just like what we saw earlier. But before the update, I will execute this function. And so we'll give it a go. Here we have our table departments and so forth and so on. And now I'll make some updates to Sunnyvale and so forth. And this begin transaction or commit, there's some type of setting for auto commit. So I just had to comment that out. Let me just put this up. Yeah, and so we'll have these basically two different updates occurring, and then we'll see here that the timestamp exists. It's been updated as part of that trigger for these. And they should be about 3 seconds apart, right, based off of that, the two different times. And there are other things like materialized views. I talked about views earlier, but we also support in this version of YugabyteDB materialized views. Materialized views can be really helpful for query performance, especially if we have aggregated data that we know people are going to look at on a daily basis or something like that. You can run some type of job to refresh the materialized view. So here's an example. So this is the main query. We're going to put it as in a materialized view for reports, sales per department. And then I can drop or create an index on this if I wanted as well. Salary per department, which was one of these values that I have here, the sum, and if I'm going to do some type of query based off of that range or something like that. But I can refresh this materialized view as well, and then query it. So anyhow, so that will help with this type of querying execution plan. It should show using that index scan backwards using that materialized view. Yeah, the recordings are going to be available. No worries. They'll be available on the DistributedSQL.org site for this summit, as well at the university course. We'll put them in both places, especially for this session. Thanks for asking. Okay, we're almost all done, at least with this section. So really, the last things I want to talk about are, and I'll go over to this sort of advanced one that I have here, is about table partitions and the like. Let me make sure I can grab everything here. Sure. So I'm going to jump onto another notebook that I have. And in this case, I'm going to bring in some data about orders that I have here. And let's just take a look at what that order, the table looks like. So we'll describe some of these tables after we bring them in. I had table cities, apartments, orders, but now you can see I have order changes, and I have three other tables here. These are actually table partitions in Postgres. So typically in Postgres, a table partition has to do with storage. Oh, I have orders for February or March. I want to store them on this disk, or I want to move them or migrate them or get rid of them for whatever reason. But our implementation in Yugabyte, we support that, is going to be different because it's going to help us with geo-distributed data. So for example, we can have a partition of data and use it to store data in our cluster topology. Rather, it's sort of the same concept, but rather than on that disk, on nodes that live in a specific region or placement block. So I showed you that earlier, that these tablets basically get assigned to these different placement blocks, and I had cloud 1, cloud 2, cloud 3. We can essentially do the same thing with the construct of table partitions and what we call table spaces. That's where I'm going with this. Anyhow, here are the table partitions that we see here. So here's my table that I have, and then I have here on order changes, and we created something called a partition key on change date. And if I look at this here, let me comment this one out, and you'll see here for this table partition 2202, it's partition of, and it has a specific vet of ranges that we have, right? Starting inclusive and exclusive from this range. So any of those values will be stored in this table partition and so forth. So anyhow, I'm going to use this auto commit feature, and then let me connect here, and I'll use this connection. And now I'm out of bash, and we can select from order changes. So this is the logical table order changes. I can insert data into that table, either one, but I could also do things like query the individual table partitions as you see them listed here. And these, and just to look at real quickly, and I'm pressed on time, but let me just see if I can hop over here as we look at this onto my host, onto our tables. So we have our table, in this case, order changes. So we have, this is the quote unquote logical table that we have, right? And we'll show that it has like partitioned like tablets, but really these table partitions, these are the ones with the real tablets that we have here. So these table partitions exist as tablets. That's the takeaway. And they'll belong, if we want to, using table spaces to one of these table blocks. So that's where oh yeah, so you can create an index on order changes like this and so on. You can drop one of the table partitions and so on and so forth. All those standard features that we do with PostgreSQL. So where things are different, like at this point in time, this is the last 10 minutes, I've shown a high degree of PostgreSQL compatibility. But now let's talk about like why Yugabyte's different. Let's create a table called table transactions, and I'll use partition by list. And that's one of the options that we have, right, for how you want to partition your data on this column called geo-partition. In that case, so that's how we're going to create this, and this table transaction. Now, before I create the table partitions, what I'll do is I'll create a table space. And this table space, more than one table partition can go into it from a given table. So it can't just be transactions, it could be orders, it's like whatever. But this table space is basically arbitrarily named, but it's saying, hey, I want everything to go. I want one replica here in this placement block, cloud 1, region 1, zone 1, and so forth. And then I have another one for EU. You're going to go into cloud 2, region 2, zone 2, and so on and so forth. So for those of us who are concerned with regulation or GDPR, you have to have data locality, or if you're working with distributed systems where you have to have data locality based off a specific region, whether it's the East or the West, or like, you can do that with YugabyteDB really easily using table partitions, table spaces, as we'll see in a moment. So I'll create these table spaces that we have here. So I have these 3 table spaces here that we have. Let's take a look here, what happened. So you'll see here, I have this table space for Asia Pacific, European Union, and the United States. Now I can create my table partitions just like I did earlier with orders, but I have one for transactions for the US, I have one for EU, and I have a create a table, a key, and it's a partition of the transactions table that we have here. The one for US gets assigned for values. Remember that partition table was based off of the list of values of geo-partition and within tablespace US. And that's going to be the same here. Values EU go into tablespace EU, India goes in, and so on and so forth. So I'll run those. All right, and then we'll add some records. So this first row should end up into the table partition in the table space for US. This will go into a table partition for EU in the table space for EU, and so on and so forth with India. And I can validate that. So logically speaking, all the transactions are here. But I can query each table partition, and I'll see the individual rows that we have by design. But then I can also look at what we call the table ID, in this case for like transactions. And this will show that these 3 rows belong to this tablet ID, transaction EU, and so forth. So let's just take a real quick look then. If we go back over here and refresh and only find transactions. Here we go. So for transactions, so I'll just go to the one here for US, and you'll see here, this is the table space it lives in. That's what that definition created for the table space. Whereas transactions for Asia Pacific are in Cloud 3 regions, Zone 3. Yeah, and so now, and if my cluster wasn't local, actually those things lived in those areas. That's where they would live in a geo-distributed database like YugabyteDB. That's exactly how it works. Okay, cool. So that's all I wanted to show in terms of my demonstration for today. I do have some slides about how this works in terms of partitioning, but I think the demo pretty sums it up. As I mentioned, like partitions are also tablets, right? So they get sharded, replicated. And the partition types, you have like range, list, or hash. I showed you list, but you could also do range or hash. And based off of a value that you define, as people insert data or update data in a specific table behind the scenes, the database handles where the data actually gets stored in the table partition in YugabyteDB. That's a distributed table, so to speak, that consists of tablets and so on. So that's pretty straightforward. And we looked at all this default partition. And you can index the partitions as well. I didn't show that. And drop or remove those partitions as needed, create partitions, and so on. And then with table partitioning and geo-distributed data, we'll take advantage of something known as a table space, where it's like essentially associated with like a location for storing data. But we do it in the context of our cluster topology, our placement information. So we can do that. So with row level geo-partitioning, we could have something like we did our transactions table or user table in this case, where we're using that partition key as a way of defining just not the table partitions, but also assigning that to a specific table space. And that table space lives within a specific cloud region and zone. Right? You have geolocation for US, geolocation for European Union, geolocation for India. That's what I demo gave an example of how to do. Again, setting it up was pretty straightforward. Here's an example of our transactions table using a list of the values of geo-partition. And we created our table spaces. Essentially, what's of concern with us is not storage, but where that space is. So where the nodes are that belong to a specific cloud region and zone that we have. And then and this can be more complicated, right? So if I have more nodes and so forth, I can define this with more replicas and the like. So it can get very, very complex if you so desired. And then we define those table partitions, right? And they're basically assigning those partitions with a specific value to the table space. And you insert data just like you normally would into transactions and all, and then you can query either of those table partitions or the table itself, right? And so forth. So that's how you can list the table spaces. Cool. And this is one way that you can build applications to access this data. yeah, you can have a geo-distributed cluster topology. I have some extra slides here to help with this. You can do things like have read replicas as well. And you can have applications using smart drivers that will know which region that they're accessing and can connect to within really the DB ecosystem. So some flexible deployment options that you have here, just a high level if you're interested, like variety of options that you have with YugabyteDB. Some of these that's like X cluster and beyond the scope of this course, but I just wanted to share these with you because we have lots of customers who have a really, I would say, a pretty robust geo-distributed cluster topologies, whether they're multi-zone, if they have single direction async replication, or bi-directional async for above connection between two clusters that they have, lots of different configurations. So just make sure that they're resilient. We had one of our folks on our team coming over from Ireland, and they had an outage with their airline provider that was a cloud provider outage, and they're out for 2 hours. If that company had used a geo-distributed database for their ticketing system, they wouldn't be dependent on a certain region in AWS going down where nobody can get on a plane for 2 or 3 hours until that zone recovers. Like that worked 10 years ago, but I think in today's era, you can't be beholden to one single cloud provider or just one data center. You have to build geo-distributed applications and to really weather all the storms and outages that seem to be occurring on a daily basis nowadays for your mission critical and business critical applications. Okay, so thank you everybody very much for your time today. I really appreciate it. Yes, we'll have the recording available